All right, let's talk about numerical integration. The the idea here, and by the way, I'm skipping section 6. Section 6 is all about how to use software to compute integrals, and I don't think I need to show you guys that because half of you are already doing that for the tests and quizzes, which you shouldn't be doing. But anyway, but yeah, that's just a technology thing, and you can kind of pick that up. It's not difficult to use technology to calculate integrals and stuff. But Chapter 7 has some good information in it. It's a very dense section. I think it's like 10 pages long. So I'm going to try to just give you the Cliff Notes version of Section 7, because I do think that there's some important stuff in here that you should know about. But anyway, the idea is that in this chapter so far, and also in Calculus 1, we've been building up all of these strategies for doing integration. And so, it may lead you to believe that, we can now integrate anything that's thrown at us. But that's not necessarily true. For example, like if you had this sort of situation, e to the x squared, just that. We don't have any techniques for integrating that. I mean, there are more integration techniques than what we cover in this class, and so there might be integration techniques out there that'll help you handle this. But so far in this class, we don't have any techniques that help us handle this. And ultimately, no matter how many techniques you build up, you're always going to run into functions that you just can't find closed formula for integrating them. And so when we run into scenarios like that, we rely on approximations, right? And we call those things numerical integrations, right? So we rely on like Riemann sums and stuff to get approximations for what those integrals should be. And you already have done some of this in Calculus 1, right? So in Calculus 1, you went over the left endpoint, right endpoint, and midpoint approximations for integrals. And there's a nice table in your book that summarizes that stuff. It's on page 455. This is page 455, and this is table 7.7.1. So here you have the left endpoint approximations. So you can see for each rectangle, you're using the left endpoint as the height of the rectangle, right? And this is the formula that you would use. By the way, throughout this section, y always refers to f of x, right? So y1 is f of x1, where x1 would be this right here. So y1 is f of x1, right? Anyway, so that's left endpoint approximation. Right endpoint approximation is here. And then midpoint approximation, where you take the midpoint of each interval, right? Looks like this. And so you've seen that already. You've seen that in the past. For the purposes of this lecture, and this class really, we'll use this notation. So Ln is going to be the left endpoint approximation with n subintervals. Rn is going to be the right endpoint approximation with n subintervals, and Mn is going to be the midpoint approximation with n subintervals. Okay. So what I want to do in this section is show you two more approximation techniques that you haven't seen before. One of them is the trapezoidal approximation, and the other one is Simpson's rule. Okay? So for the trapezoidal approximation, let's just remind ourselves that the area of a trapezoid is 1/2 times height times base 1 plus base 2. So in other words, if you've got some kind of like trapezoid, right? That was very poorly done, but these should all be straight lines. Anyway, the idea behind the trapezoid is that you've got two parallel lines, in this case the top and the bottom, and those parallel lines, we call those base 1 and base 2, and then the distance between the parallel lines is the height of the trapezoid, right? And so the area is 1/2 times height times base 1 plus base 2, right? That's the way the area of a trapezoid works. Now in our case, our trapezoids are actually going to look more like this, right? Because what we're going to have is a whole set of trapezoids, right, that are meant to kind of try to approximate the value of the function. So in this case, this would be like base 1, this would be base 2, and this would be the height, right? But still, the area is 1/2 height times base 1 plus base 2. So, so that's how the area of trapezoids work. So the trapezoidal approximation then of an integral, we're going to denote that by t sub n, right? And it's 1/2 times height, right? B minus a over n, that's the width of each of these little trapezoids, or the height of each of these trapezoids. So it's 1/2 times height times, and then this is maybe a little confusing, but check it out, right? So so to do the area of this first little trapezoid, you would do 1/2 times height, which is b minus a over 2, and then times b1 plus b2, so times y naught plus y1. And then for the next one, you're going to do 1/2 times b minus a over n times y1 plus y2. And then for the next one, you're going to do 1/2 times b minus a over n times y2 plus y3. And so each of these things gets repeated, except for the very first one and the very last one. The rest of them will all get repeated, which is why here we've just factored out the 1/2, and we've factored out the height, b minus a over n, and then we're adding up each of these things, but the ones in the middle all get doubled, right? Anyway, so that's the trapezoidal approximation. Now, another cool thing about the trapezoidal approximation is that it's actually the average of the left endpoint approximation and the right endpoint approximation. So if you already knew the left endpoint and right endpoint approximations, then you could just find their average, and that would be the trapezoidal approximation. Okay, so that's how the trapezoidal approximation works. And I'll give you an example of this in a second. Okay, but let me give you the other approximation that I want to go over in this section, and it's called Simpson's rule. Simpson's rule is kind of crazy, and by the way, if you're interested in seeing the derivation of this formula and all of that, you're welcome to read the textbook. I'm just going to give you the results. But Simpson's rule, we're going to denote the Simpson's rule approximation by S sub n. And Simpson's rule says that we can approximate this integral by doing 1/3 times 2 times the midpoint approximation plus the trapezoidal approximation. Notice the subscripts here, right? So here, if we're going to use n subintervals for Simpson's rule, then we use n over 2 subintervals for the midpoint and trapezoidal rules. So to give a concrete example, right? Like if we wanted to do 10 subintervals for Simpson's rule, so if n is 10, then we would do 5 subintervals for the midpoint rule and 5 subintervals for the trapezoidal rule. And the reason for that is because Simpson's rule uses both the endpoints and the midpoints, right? So if you're imagining like laying out Simpson's rule, it would look kind of like this, right? So one subinterval would actually go from x0 to x2, and so the width of each subinterval is actually 2 times b minus a over n, right? So because b minus a over n just gets you from the left endpoint to the midpoint, right? And then another b minus a over n would get you from that midpoint to the right endpoint, okay? But all of the odd subscripts are actually midpoints. Anyway, so just be careful with that when you're using Simpson's rule. Again, I'll give you an example. So that's one formula that we could use to compute Simpson's rule. Now, this requires you to know what the midpoint and trapezoidal approximations are going into it. So if you didn't know what those things were, and you didn't necessarily want to have to compute them before you tried to use Simpson's rule to approximate this integral, well then you could use this formula, and this is formula 8, right? So this one's formula 7, this one's formula 8, right? So formula 8 says that Simpson's rule is 1/3 times b minus a over n times, and now this gets really crazy, but it's y0 plus 4 times y1 plus 2 times y2 plus 4 times y3 plus 2 times y4. So it goes 4, 2, 4, 2, 4, 2, 4, 2, 4, and then 1. So the endpoints are just one copy, and then in the middle it alternates 4, 2, 4, 2, 4, 2. So kind of an interesting formula. Again, you can read the textbook if you're interested in the derivation of it. But And as usual, right, the yi is f of xi, right? So you plug it in here to f of x. So let's look at let's do a couple examples. Okay. So the first example I want to do is to calculate the midpoint and trapezoidal approximations for this integral, which, by the way, we know the exact value of this integral, so it's kind of silly to do approximations for it, but that's all right. Anyway, we're going to do the midpoint and trapezoidal approximations for this integral, and then we'll use those, m5 and t5, to calculate s10 using formula 7, using this formula here. Okay, so let's do that. Okay, so the integral that we want to approximate is this. Integral from 1 to 2 of 1 over x dx. Okay, so for m5, that's the midpoint approximation. So for the midpoint approximation, m5 is b minus a over n times the midpoint of each interval. Now, if we're going to break this down into 5 subintervals, then that means, so notice that this is 1/5, right? So each interval has width 1/5. So the midpoint, so maybe if I draw a picture, it would help, right? So if I'm breaking this down, and here's 1, I've got 1 1/5, 1 2/5, 1 3/5, 1 4/5, and then 1 5/5 too, right? So this breaks it down into 1, 2, 3, 4, 5 subintervals, right? So this is going to be 1 plus 1/5. This is going to be 1 plus 2/5, 1 plus 3/5, 1 plus 4/5, right? And then 1 plus 5/5 is 2. So, okay, so 1 1/5 is, of course, 6/5. So I'm just going to call this, so 1 over 1. Midpoints. Oh, that's right. So I'm doing midpoint. So I've got to get the midpoint. I've got to find actually what's this value right here. So what's right in between 1 and 1 1/5? Well, I'm going to use my calculator, right? So the average value of 1 and 6/5, we'll call it 1 plus 6/5 divided by 2 is 11/10. So my first midpoint is 11/10, and I'm plugging it into f of x here, right? So 1 over 11/10 plus, what's the next one? It's going to be right in between 6/5 and 7/5. So 6/5, 6/5, and 7/5 divided by 2. It's 13/10. So this is going to be 1 over 13/10. Okay, and then I think I see how this pattern is going, right? 1 over 15/10, 1 over 17/10, and then 1 over 19/10, right? 20/10, of course, would be 2, so 19/10 is right between 18/10 and 20/10, so that makes sense, right? Okay, so there's the midpoint approximation, and you can plug that into your calculator now, of course. So, right, so this is going to be 1/5 times 10/11 plus 10/13 and so forth. So 1/5 times 10 over 11 plus 10 over 13 plus 10 over 15 plus 10 over 17 plus 10 over 19. I'm going to round to, let's round to maybe 6 decimal places, so I'll say it's 0.6 69198 approximately, right? So if we round to 6 decimal places. Okay. I'm just double checking. Let me show you what I put into my calculator so that if I made a mistake, you can see what the mistake was. But yeah, that's 1/5. 10 11ths, 10 13ths, 10 15ths, 10 17ths, and 10 19ths, okay? So that's that. By the way, we know that this integral is ln of x. So it would be ln of 2 minus ln of 1. ln of 1 is 0. ln of 2... ln of 2 is that number, so, you know, we're close. Anyway, so there's M5. There's M5. Now, what else were we supposed to do? We were supposed to calculate M5 and T5, so let's do T5. So trapezoidal rule. Trapezoidal approximation. That's this one right here. Okay. This one's a little easier because we're not working with endpoints anymore. We're just going to be working, or sorry, we're not working with midpoints anymore. We're just working with the endpoints, which is kind of nice. Okay, so it's going to be 1/2 times b minus a over n times y1, so that's my, or sorry, y0, so that would be f of x0. X0 would be 1, right? So this is 1 over 1 plus 1 over, if I add 1/5, 1 plus 1/5 is 6/5. Plus 1 over, if I add a 5th again, I'm going to get 7/5. Oh, I'm sorry, and I've got to double these ones, too. Plus 2 times 1 over 8/5, plus 2 times 1 over 9/5. And then when I get to 10/5, I'm at my other endpoint. And that one I do not double, right? I don't double the right endpoint. I only double the ones in the middle. So I'm just going to say plus 1 over 2, right? Because then I've gotten to the end. Okay. And notice now, here I had 5 terms, 1, 2, 3, 4, 5. Here I have 6, 1, 2, 3, 4, 5, 6, because I've got each of the endpoint, the very leftmost endpoint and the very rightmost endpoint, and then the four endpoints in the middle, I guess. Anyway, so let's see what we get here. So I know 2 minus 1 over 5 is 1/5 times 1/2 is 1/10. So I'm going to get 1/10 times 1 plus, if I flip and multiply, that's going to be 10 over 6. Which could reduce, but my calculator is going to do the heavy lifting in a second. So plus 10 over 7, plus 10 over 8, plus 10 over 9, plus 1/2. Okay, let's see what that is. So here goes nothing. This is always nerve-wracking to me. This kind of stuff is always nerve-wracking because I feel like I'm going to make a mistake. I just know it. Right? I just know I'm going to make a mistake. But let's see. So 1/10 times 1 plus 10 over 6 plus 10 over 7 plus 10 over 8 plus 10 over 9 plus 1/2. And yeah, that seems reasonable. Okay. So this is about 0.695635-ish. Okay, so there's the trapezoidal approximation. Very good. Now, what else were we supposed to do in example 1? We were supposed to find M5 and T5 and then calculate S10 using Formula 7. Well, Formula 7 says that S10 should be 1/3 times 2 times m5, right, plus t5. And I've already done those, right? So m5, so this is approximately 1/3 times 2 times 0.691908 plus t5, 0.695635. Okay? And let's see about how much S10 is. So 1/3 times 2 times 0.069198 plus sorry, made a little typo, plus 0.695635. Okay, so there's that one. So it comes out to about 0.693150. Okay, so that's how that one works. Okay, that's how Simpson's rule works and how the trapezoidal approximation works. Okay. So let me give you another example. So this was using Formula 7 to calculate Simpson's rule. Let's calculate it using Formula 8, right? So let's say that instead of asking you to calculate the midpoint and trapezoidal approximations first and then asking you to use Simpson's rule, let's say that you were just asked to find Simpson's rule. Okay, in that case, it would be a lot less work to just use Formula 8 than it would be to find these two and then use Formula 7, right? It's going to be a lot less work to just calculate S8 directly. So let's do it. Same function. Same function. Let me grab a fresh sheet of paper. Okay, so we want to calculate S8 for the integral from 1 to 2 of 1 over x dx. Okay, using Formula 8 this time, so that we don't have to find the midpoint and trapezoidal approximations first. So let's remind ourselves what Formula 8 looks like. Okay, so Formula 8 is this bad boy here. Okay. Okay, so here goes nothing. So S8 is going to be 1/3 times b minus a over n is 8. And then we're going to do starting from 1 and then ending at 2. And we're going to split that into, in this case, we want 8 subintervals, right? So it's going to be 1 over 1 plus 4 times 1 over, what would the next one have to be? Well, if I add an 8th, right? If I add an 8th, I'm going to get 9/8. Okay, and then 2 over, it's going to be, if I add another 8th, it's going to be 10/8 plus 4 over, if I add another 8th, it's going to be 11/8. Okay, 2 over 12/8, 4 over 13/8, 2 over 14/8. How far should I go? So I've got 1, 2, 3, 4, 5, 6, 7, 15/8, and then 16/8 would get me to 2, right? So that's where I'm going to stop. So plus, and that one I don't multiply by 2 or 4. I just have 1, right? It's just 1 over 2. Okay, so let's plug that mess into our calculators. We can clean it up a little. 2 minus 1 is 1. 1/8 times 1/3 is 1/24. 1 plus 32/9 plus 16/10 plus 32/11 plus 16/12 plus 32/13 plus 16/14 plus 32/15 plus 1/2. Okay. So I've got 1 over 24 times. I'm going to do this here so that you can catch me if I make any mistakes, because we're not in person, and so you're not going to be able to tell me in class if I've made a mistake. But 1 over 24 times 1 plus 32 over 9 plus 16 over 10 plus 32 over 11 plus 16 over 12 plus 32 over 13 plus 16 over 14 plus 32 over 15 plus 1/2. Okay, that's reasonable based on all of our previous estimates, right? So that comes up to about 0.693155. Okay, so that's that one. Okay, at this point, I want to point out that if you're using some kind of numerical integration technique, you're most likely not going to be doing it by hand, right? For exactly the reasons that, like, we're so liable to make mistakes when we do stuff like that by hand, when we're doing those kinds of tedious calculations by hand. So on the homework, I'm really only planning on giving you a couple of homework problems so that you can practice doing this stuff, because, I mean, they're very, very tedious, right? But it's important for you to understand the formulas, understand how to use the formulas, right? And then, like, in your professional life, if you ever encounter a situation where you have to do some kind of numerical integration, well, of course you're just going to use some kind of software to do that for you. Okay, but I'm not going to show you any software. I mean, this is a math class, right? Not a computer programming class. Anyway, but one thing that I do want to talk about is which approximation is the best. And the honest to goodness truth is that it's not always easy to tell which approximation is best. Simpson's rule usually gives the best result, but not always, right? But it usually gives the best result. The midpoint approximation is usually better than the trapezoidal approximation. Well, not usually, actually. It's better than the trapezoidal approximation as long as f is strictly concave up or concave down on the interval that you're integrating over. So, however, if the function f changes concavity over this interval, then, you know, your guess is as good as mine as far as which of these approximations is going to be better than the other. But generally, we gauge how good an estimate is by calculating its error, and the errors are pretty straightforward, right? The error for the midpoint, so EM, the error for the midpoint approximation is just the actual value of the integral minus the midpoint approximation, right? So it's a pretty straightforward thing. Same thing for the trapezoidal error. It's just the actual value of the integral minus the approximation for the trapezoidal approximation. And for Simpson's rule, the error for Simpson's rule is the actual value of the integral minus the Simpson's rule approximation, right? So these things are called the errors for each of their respective approximations. The absolute errors would just be the absolute values of those errors, okay? Now, you may notice that these calculations are going to work perfectly well as long as you know the exact value of the integral. But if you know the exact value of the integral, then why bother with the approximations in the first place, right? It's kind of nonsensical. So in practice, these formulas are usually not used. Instead, we have other formulas that we can use to get upper bounds on what the errors would be. And I'll show you some of those in a second. But what I want to do for now is just practice using these, just for the sake of completeness, to calculate the errors and absolute errors for the approximations in example 1. So I've still got those. So let's do it. So in example 1, we found M5, T5, and S10. In order to find the errors of those things, we have to actually compute the actual value of this integral and then subtract each of the approximations from that integral, right? So it's not a terribly complicated thing, but let's just remind ourselves, right? So we're doing integral from 1 to 2 of 1 over x dx. So that's going to be ln of absolute value of x evaluated from 1 to 2. So that's just ln2 minus ln1. ln1 is, of course, 0, so that's ln of 2. Right, so that's the actual value of the integral. So then the error for the midpoint approximation is going to be integral from 1 to 2 of 1 over x dx minus m5. We did m5 in example 1, so we'll use 5 rectangles for that. Okay, so this is, now here I didn't save the exact value in my calculator, so I'm going to say this is approximately, well, I know that this part is ln of 2, and this part was approximately, m5 was approximately 0.691908. And so then I can give the approximation for that error. So I'm going to do, so we've got ln of 2 minus 0.691908. That comes out to 0.001239. Okay, approximately. So we're pretty close, right? I mean, this is pretty close to the exact value. So it's not bad. That's the error. The absolute error would just be the absolute value, right? Which, you know, this was already positive, so they're the same number, 0.001239. So this is the error, and this is the absolute error, which happened to be the same thing in this case, since the error was already a positive number. Okay, so that's for the midpoint. We want to do this for the trapezoidal and for Simpson's rule as well. So the error on the trapezoidal rule is going to be integral from 1 to 2 of 1 over x dx minus t5. So that's approximately ln of 2 minus, for the trapezoidal rule, the approximation we got was 0.695635. And we can punch that into our calculator. So we're going to have ln2 minus 0.695635. That comes out to negative 0.0024888. Sorry, not 89. 456. Yep. Okay. So then the absolute error is about positive 0.002488. Okay? And then finally for, well, so you can see, right, in this case, midpoint formula is better than trapezoidal. And that makes sense because 1 over x does not change concavity between 1 and 2. So it makes sense that the midpoint rule is giving us a better, right, the error is smaller is what I'm saying. So it's a better approximation. Midpoint rule is a better approximation. Okay. Last one, Simpson's rule. Let's see if this one's the best. So error for Simpson's rule is going to be integral from 1 to 2 of 1 over x dx minus S10. So that's about ln2 minus 0.693150. So ln2 minus 0.693150. Yeah, I would say that's better, right? So that's about negative 0.123452345 So it's a good thing we've been rounding to 6 decimal places, or else we wouldn't have even seen what the error was here. We would have said, oh, it's error 0. Yeah, Simpson's rule gives us a very nice approximation, right? Anyway, absolute error for Simpson's rule is about 0.123453. Okay. So that's how we compute errors and absolute errors. But once again, these calculations only work if you already know the exact value of this integral. And if you know the exact value of the integral, then why in the world are you bothering trying to approximate it, right? So what's more likely is that we don't know the exact value of this integral. And in that case, though, we can still get upper bounds on the errors as follows. So these are kind of cool formulas. And this will take you back to your Calc 1 days a little bit. But here's how this works. And again, I mean, the proofs, I'm not even going to try to give you the proofs for these things. But and another thing is that you're never going to remember all these formulas, right? So like you're welcome to use your notes on tests and quizzes for like, especially for this section. But anyway, if f double prime is continuous on the closed interval AB, and if k2 is the maximum value of absolute value of f double prime of x on AB, then the error for the midpoint approximation is always less than or equal to this quantity, b minus a cubed times k2 divided by 24 n squared. Error for the trapezoidal approximation is given by this thing, which is the same as the midpoint, except that you're dividing by 12n squared instead of 24n squared, which is interesting. Okay. And then for Simpson's rule, we have to go up to the fourth derivative, right? So if the fourth derivative of f is continuous on AB, and if k4 is the maximum value of the absolute value of the fourth derivative on AB, then the error for Simpson's rule is always less than or equal to this monstrosity, right? b minus a to the fifth times k4 over 180 n to the fourth. So let me show you these formulas in action. Actually, I'm not going to do 12 because it's very similar to 13. But let's do formulas 13 and 14 to find upper bounds on the error for the trapezoidal rule and the error for Simpson's rule if we're using 10 subintervals here. Same 10 subintervals here, but because you're using both endpoints and midpoints, we call it S20, right? But same number of subintervals. Anyway, so let's find the upper bounds on the errors if we're using these to approximate this this integral. Okay. Now the good news is that in order to do that, we don't even need to find out what these errors are. Okay. All we have to do is find K2, or K2 in the case of formula 13, and K4 in the case of formula 14. Everything else we already know, right? We know what n is, right? 20 here, 10 there, and we know what b and a are for 9 and 4 respectively. So I just need to find K2 and K4. K2 is the maximum. K2 is the maximum value of f double prime of x. K4 is the maximum value of the fourth derivative of f of x. So let's work that out. This is f of x, by the way. F of x is 1 over square root of x. Which you'll notice is, once again, this is once again an integral that we already know how to compute. So this is kind of a silly example, but I didn't want to do this with a nasty one. Like the kinds of things that we can't compute the integrals of are nasty. So I didn't want to give you such a nasty example, but we'll do f of x equals 1 over square root of x. So this is what we're doing here, 4 to 9, 1 over square root of x dx. And we're really just interested in finding the errors for the trapezoidal and Simpson's rule approximations. So f of x is 1 over square root of x. I'm just going to call that x to the negative 1/2 power. And then I'm going to take a bunch of derivatives of this thing. So f prime of x, right? Because I want to find the maximum value of f double prime, which means I need to go to f triple prime at least, right? If you remember back to your Calc 1 days, so f double prime is 3/4 x to the negative 5/2, and then one more. By the way, this only works if f double prime is continuous. Well, continuous on AB. AB in this case is 4, 9. And yeah, you're not going to run into any problems. The only place you'll have problems is when x is 0, because then you'll have a 0 in your denominator, right? But you don't have a problem there, so this is continuous. So yeah, so we look at f triple prime, and that's going to be negative 15/8 x to the negative 7/2. Okay, so if I want to find the maximum value of f double prime of x, what I need to do is find the critical values of f double prime. The critical values are going to take place whenever f triple prime is either 0 or undefined. And f triple prime is going to be undefined whenever x is less than or equal to 0, right? Because this is negative 15 over 8. Oh, how should I write this? I'll write it like this. 8 times the square root of x to the 7th power, right? So you have issues whenever x is 0, because then you have a denominator of 0. And you also have issues whenever x is negative, because then this is not a real number. It's a complex number in that case. But on the interval from 4 to 9, we don't have to worry about either of those things, right? So we would say, we would say a critical value is x equals 0. But x equals 0 is not even in this interval, so we don't have to worry about it. So then to find what the maximum, value is for this function on this interval, we just plug in the endpoints, right? 9 and 4. So I'm going to say f double prime of 9 is, goodness, I'm just going to punch this into my calculator. I mean, square root of 9 is 3. 3 to the 5th is, I don't know, something. So 3/4 times 9 to the negative 5/2 is 1 over 324 Okay, f double prime of 4 is, if I go back and put 4 in there, 3 over 128. So which of those is bigger? Yeah, so this one is bigger, right? So this is our maximum value. Right? That's our maximum value. So this is equal to, so K2 is equal to 3 over 128. Okay. Now, before I calculate the errors, let me just calculate, right, so I needed K2 to calculate the error for the trapezoidal rule, but I also need K4 to calculate the error for Simpson's rule. So I'm just going to go ahead and do that, right? So while I'm kind of on a roll here, right, this is going to be, oh goodness, 7 times 15, whoops, 105. So this is going to be 105 over 16x to the negative 9 halves. And again, this is continuous. The fourth derivative is continuous on the interval from 4 to 9. Because the only place it's going to be discontinuous is if x is less than or equal to 0. But between 4 and 9, we're good to go. So it's continuous. So if I want to find its maximum and minimum values, they could occur either at the endpoints of the interval, or they could occur at a critical point somewhere in between. The critical point is going to take place whenever the derivative of the fourth derivative, in other words, the fifth derivative, is 0 or undefined. 9 times 105 is 945. So this is negative 945 over 32x to the negative 11 halves. Wow. Okay. Now the good news is that might seem kind of complicated, but again, the only critical value you're going to get is when x equals 0. Okay? And right, so the only critical value is x equals 0, which is not even in this interval, so we don't have to worry about it. That means that the maximum and minimum values are going to take place at the endpoints, right? So I just have to plug in 9 and 4, and I'm going to guess, based on my previous work, that the maximum value is going to take place at 4, right? Because it's a decreasing. Yeah, I mean, I suppose I could have saved myself some work and realized that, 1 over square root of x has got to be a decreasing function, right? It's got to look kind of like that, I suppose. So yeah, I'm going to go ahead and say that the maximum value, right, the maximum value, K4, is going to be the fourth derivative of 4, which is going to be 105 over 16 times 4 to the negative 9 halves. And that comes out to 105 over 8,192. So there's K4. Okay, so I've got K2 and I've got K4, so I can calculate my errors now, right? So error for the trapezoidal rule, or absolute error for the trapezoidal rule, is less than or equal to b minus a cubed, so that's 9 minus 4 cubed, times K2, that's 3 over 128, divided by 24 times n squared. N for the trapezoidal rule is 10. So times 10 squared. Okay? So let me just punch that into my calculator. I'm going to open up a couple set of, actually 9 minus 4 I can just do in my head. So that's just 5. So 5 cubed times 3 over 128. Maybe I'll put it like this, times 3 over 128. All over 24 times 10 squared. Yeah, I think I got that in there. I think I got that in there correctly. So that comes out to 5 over 4,096. Okay. So I know that the error for my trapezoidal rule is going to be less than or equal to this number, which, by the way, how much is that approximately? That's about 0.00122. Okay? So it's going to be less than or equal to this number. Cool. All right. For Simpson's rule, this was for n equals 10. For Simpson's rule, if n is 10 in the trapezoidal rule, then it's 20 for Simpson's rule. Okay? That's going to be less than or equal to b minus a to the 5th power times k4, 105 over 8192, divided by 180 times n, which is 20, to the 4th power. This is going to be a tiny number, I feel. Okay, but let me punch that into my calculator. So I'm going to have, it's going to be 5 to the 5th power times 105 over 8192 all over 180 times 20 to the 4th power. Okay. So that comes out to about 0.12345. Okay, so that's pretty cool. So I know that whatever my Simpson's rule estimate is, it's going to be within, it's going to be really, really close to the actual value of the integral. And in this case, again, I could compute the actual value of this integral. But it's nice to know that I could do this even if I weren't able to compute the actual value of the integral, right? So that is all I have to say about this section. And I think I've said plenty. But again, your book has a lot more information here. If you're interested in this kind of stuff, you should take a course called what's it called? Numerical measures or something like that. Numerical integration, numerical analysis is what it's usually called. That's what it's. I had a hard time thinking of that, but yeah, numerical analysis. All this stuff is numerical analysis. So you can take an entire course talking about this kind of thing. So anyway, that's that.